All right, glorious class, let's go ahead and start chapter 8a. Oh my goodness. So remember last time we talked about SN1 and SN2 reactions. Today we're going to learn two more reactions that kind of follow in some similar footsteps. So hopefully that helps us remember them. And actually it will make the lecture go a little more smoothly than the last one, I think. Okay, so getting started, we are going to learn E1 and E2 reactions. E1 and E2. We're going to first talk about E2. E2, we'll get into it in a second, but the E, I should say, stands for elimination. And if you remember from chapter 5, we talked about when you eliminate some things in an elimination reaction, you end up with a double bond. Or maybe if you start with a double bond, you end up with a pi bond, or with a triple bond. We also briefly covered this in the last chapter, where we said that we're going to have a base. Anytime we react something with a base, it's going to attack a hydrogen. And that hydrogen bond is going to come down and make a double bond, and the leaving group leaves. Now, I'm not drawing a mechanism yet because there's two different mechanisms for which that can occur, but the premise behind it is that you're always going to end up with a double bond, and that H and X, the H is attached to the base because remember, base is like hydrogen, and the X is going to be off on its own because it's cool to hang out on its own. So let me give you an example real quick. So let's say we have something like, I'm going crazy here. I don't know why I drew so many peaks, but whatever. And let's react this alkyl halide, because we're all talking about alkyl halides still. For SN1, for SN2, for E1, for E2, it's always going to be a bromine, fluorine, chlorine, or iodine that we're talking about. And this thing is going to react with a base. So like K plus, and then the base would be like OCCH3. So you've got this like almost T-butyl looking thing. Like that, okay? And it's got a K plus just kind of chilling. Now, generally we can ignore the K plus, and that would be a negative, by the way. This whole part would be the negative. Generally we can ignore a K plus, and you'll kind of get used to doing that here in a little bit. But for this first one, let's just write what you'd get as a products. You're going to lose some kind of HBr, so you'll lose a bromine from here, you'll lose a hydrogen, and what you'll end up with is that plus the H is going to go on to this thing right here. So remember that was the base. My parentheses look like C's, I know that. There we go. Plus KBr. So the H goes onto the base, and the potassium and the bromide can now hang out because you got a positive and a negative. All right, now, let's say we have, let's make this a pentane. Let's say you have a pentane and you've got a chlorine and a hydrogen. I didn't draw the hydrogen over here because it won't usually be drawn for you. So it's gonna be like this. And let's react it with sodium CH2, CH3. Okay, we're gonna lose an HCl from here. So we'll take this and that away. And what you're gonna be left with is a double bond thing there. Plus again, the H is going to be attached to the base. And the sodium and the chloride are going to chill out. And hopefully that kind of comes a little more intuitively like that. So this would be a full reaction of an elimination reaction. And again, you don't know yet if it's E1 or E2, but very similar to SN1 and SN2, there are conditions that will lead you to determine which one is which. Okay, just to get used to some common bases, sodium hydroxide, potassium hydroxide, sodium methoxide. So it's a meth oxide if it's got just one carbon, right? You can imagine it's an F oxide if it has two carbons. And there we have the tert butoxide, which would be this thing right there. Okay, so those are just going to be some common bases that will help indicate if it's going to be an E1 or E2 reaction. Okay, so when you label the carbon and the hydrogen, you'll know where that double bond is going to go. We'll get into stability. I'm actually going to kind of adjust it rather than waiting a whole long time because I think it's a pretty straightforward concept. But where that double bond goes will depend on the stability of it. So we call the carbon that's attached to the halide. We call the carbon that's attached to the halide an alpha. And then we call the carbons that are on either side of that the betas, okay? And if it happened to have a third one, which it does here, this is also beta. So notice we got 3 betas. Okay. So what's going to happen is you're going to get a double bond between the alpha and a beta. It could be here, it could have been here, and it could have been there. We don't know where it's going to go yet. Let's look at this one. So here we have again the alpha carbon, which is the one that's attached to the halide, so that would be the alpha. The betas are on either side of that. If there had been another carbon up here, that would have been a beta. And then you're going to react it with a base. The base takes the hydrogen, the bromide comes off, and you get a double bond. The question is, where do you get a double bond? Well, it must be touching the alpha no matter what. The double bond has to be touching the alpha. And it's either going to go to the beta over here or beta 2 over here. Just so you know, this is the more stable one. And that's because it's a double bond between 2 carbons, and this is only a double bond with 1 carbon attached. So the double bond, it wants company. It wants to be between more carbons. I don't know why I'm spelling between with 2 T's. I guess I was spelling better. Between 2 carbons, okay? Or more. So 2 or more carbons is really great. So the more carbons it has, the more stable it's gonna be. All right, so let's go ahead and label alpha and beta in each of these and go ahead and draw what the product would be with this base right here. Okay. I'm worried about the major product, so I'm not even going to draw the KCl, potassium chloride. This would have been potassium chloride, and this one would have been potassium bromide. As a result, we don't really need those. So each of these is going to react. All right, now the alpha is the one that it's attached to. So in this case, I'm going to zoom in a little bit here. In this case, the alpha is that one. And the beta is on either side. In this case, there's only one, so the beta is going there, okay? So you know there's only one place to put that bond. It's between the alpha and the beta. So when I go to draw it, it's going to be there, if that makes sense. So between the alpha and the beta, this is still the beta carbon. That's still the alpha carbon, and it went between those 2 things. And again, I'm reacting with the O CH3, the tert butoxide thing there. Okay. Okay, in example B, our alpha carbon has to be this one in the middle because it's the one that the alkyl halide's attached to. And our beta carbon can be one of many things. Remember, the beta is on any side of the carbon. That's the alpha. So we have a beta here and a beta here. Thankfully, they're mirror images, so they're really the same thing. And you have a beta here. So let's go ahead and call these beta 1. This could have also been beta 1, because again, this is got a mirror plane in it. And this, let's call it beta 2. Okay, when we go to draw the product of this thing, reacting with the same base up there, Again, it's going to be between the alpha and the beta will be the double bond. So we'll draw one double bond will look like this. And you could get it between alpha and beta too. Hopefully you already kind of recognize that this double bond is between two carbons. So actually this one and this one. And this one too, so it's actually 3, 1, 1, 2, and 3. And this one only has the 1. So that's why this one is more stable. You would get both products, but you'd get a majority of this product. Last but not least, we have this one. So our alpha is always going to be the one that the halogen is attached to. So it's going to be that carbon right there. And then the beta could be here, here, or here. So let's go ahead and call this beta 1. But hopefully you recognize that this is a mirror image. So this one would also be beta 1. And this would be beta 2. Okay. So, this one down. He says hi. So when we go to draw it, we're going to draw that bond between the alpha and the beta. So I'm going to draw it between the alpha and beta 1 right there. I could have also chosen to draw it down here. It would have been the same exact compound rate. And the one that's between the alpha and the beta 2. Like that. This one would be the most stable. You look to the end of the double bond, and this one's attached to 2 carbons, and this one's attached to 1. So this is what we'd call tri-substituted. This is only attached to 2. This is di-substituted. So this one is more stable. Once again, you would still get both products technically. Okay, moving on. Oh, hey, speaking of, we've already kind of been introduced to this now. Pull this up a little bit again. We've already been introduced to this a little bit, and hopefully we're comfortable with the fact that this one would be the more stable conformation because it's tri-substituted. There's even a tetra-substituted thing. So if you have like a double bond that's attached to a carbon, to another carbon, and another carbon, and another carbon, like if these are all R groups, that would be tetra-substituted. So hopefully this makes sense. You look to the carbons that are on either side of the double bond and you ask how many carbons are attached to those carbons. So in this case, I got 1. In this case, I have 2. In this case, I have 1, 2, 3. And again, in this case, I would have 1, 2, 3, 4. All right, briefly, let's kind of review cis and trans stuff. We talked about cis and trans in the past. Let me pull out a regular piece of paper here. We talked about cis and trans stuff when it came to cyclohexane, right? We said, okay, if you got something that's up and something that's down, one up, one down, we would call this trans. Whereas opposed to this, if you had them both like this, we would call this cis. We also talked about it in terms of chair conformations. We said, hey, if you've got something that's up and something that's down, so this would be like maybe over here. This would be trans. As opposed to, if you have one thing that's up, maybe another thing that's also up, this would be cis. Cool. So, all right. But I got a lot of questions about this because then you oftentimes kind of run into maybe a situation where one thing looks like it's up and the other one's down. So for example, let's say we have something like this. And I don't know. Let's draw it like that. There, maybe something like this, and then we'd have a hydrogen here and a hydrogen over here. Okay, and you look at this and you want to be like, hey, look, they're on the same exact side, right? So if they're on the same side, they should be cis. But this is a single bond, and a single bond acts kind of like a rope, or just like this pen. It can rotate around. It's got no problem in that. There's my other dog. It has no problem rotating around. So if I rotated around that bond, you might get a different Newman projection, right? The Newman projection would look different here. They're overlapping each other, and here they are not. But you're not going to get a new structure. This is still the same molecule. It's just been twisted. But if you have a double bond, like this, you can't twist this. The reason is you can't like twist two pens around each other. It's not going to freely turn. We don't turn it like this. It would have to actually literally twist around itself, and it would get all tight and screwed up. It's like a rope. It's like if you have two ropes. And because of that, that is very different. And this being the cis would be very different from the trans molecule here. So these are not the same molecule. So if you have a single bond, they're the same, but if they're on the other side of a double bond, it makes a totally different molecule, right? So that's going to be helpful to know. For example, let's look at several structures and determine if there would be a stereoisomer, if there would be another cis or trans isomer to that thing. So one of the quick ways to determine if there would be if there are two identical groups on the end of a double bond. Then that means it's not going to be cis or trans because they're going to be identical on either side. And that means no isomer is possible. So you could really think through these a lot, but I think this rule is really helpful in quickly determining if there's going to be something that's going to be cis or trans. So if you have two identical groups on the end of a double bond, no isomer is possible. Let me give you an example. Okay, so let's look at three molecules. Let's look at A. Okay, so here's our double bond. Notice you have two identical methyl groups on this side. Therefore, no, not possible. No stereogenic center is possible for A. All right, let's look at B. Let's say I kind of take that same idea. Pretty bad job drawing the double bond there. Okay, so here on this side of the double bond, I have two of the same things. So if it got flipped around, it would still be the same thing. That's the whole point behind two identical things. If you flipped it around, it would not make it cis or trans because it's the exact same thing. Okay, so this one is no. However, I got a hydrogen on this bond, and I have a hydrogen over here. Yeah, I got the same thing, but they're not on the same side. So if I flip this thing over, I'd have a completely different molecule. And it's because of that, this is a yes. There is stereogenic, or stereoisomer, excuse me. So, isomer is possible. So currently you have one thing down and the heavier group up, so this would be trans. You could also have flipped that OH down and made a cis isomer. All right, and last but not least, C. Let's go ahead and do this one. Put a methyl group there, and a methyl group there. And I'll do that. And I'll do this. Okay, so at first glance, let's look at this one. This looks like it's totally possible. And it's not right. It's gotta go right there. Doesn't make any sense. Let me redraw this sucker. Whatever I put in my notes was crazy sauce. Like that, okay? This hopefully makes a little more sense. If you flip this over, you're still gonna have a hexane, right? This and this goes to that and that goes to that. They're all identical. So it has two identical groups on it. So this one is a no. This one would have been, by the way, a yes. And now let's go to this one. If I flip that methyl group up, it would make a completely different isomer. So this is a yes. You can make a stereoisomer if you end up with a double bond and something like that. And the reason we're doing this is because when you put double bonds in your E1 and E2 reactions, you're going to want to recognize, would there be a stereoisomer that's possible? And if the answer is yes, you want to draw both of them. Okay, let's keep it going. Okay, so there are two mechanisms for elimination reactions. We got E1, unimolecular, meaning its rate only depends on one thing, and E2, meaning its rate depends on two things. We're going to start with E2, much like we started with SN2 in the last one. E2 is a one-step reaction, just like SN2 was. And our rate is going to be equal to the alkyl halide times the base. Oftentimes we would just call that an Rx. And B for base. So okay, again, what's going to happen? The base takes on a proton, so it did right here, and the bromine is going to come off, and we end up with a double bond between where there's two things to work. All right, so let's practice doing one. Again, right now we're talking about E2 reactions. E2, so a single step and everything happens. All right, so the first thing the base is gonna do is grab a proton. Remember that this is called the alpha carbon, and the beta would be here, here, or here. Hopefully you recognize that these are all identical, so it doesn't matter which beta you choose. You can choose either of them. I'm gonna choose this one because it just looks easier going left to right. All right, so the first things first, it's going to grab the hydrogen that's on that. So the base comes and it's like, give me that hydrogen. And then the bond that was on that hydrogen is going to come down here and form a double bond. And that's gonna force this bromide to come off, okay? So the oxygen grabs the H, or the base up here grabs the H, that's what bases do. The electrons from the H come down here and join up and push that bromine off. So what you end up with is something like that, okay? So before we had the going right here, and now we have a double bond right there. Now again, you could have put the double bond here or here. You could have chosen your beta to be either of those, but it would have been the same molecule, right? Okay, now what affects E2 is several different things. The leaving group, so if it has a really good leaving group, it's going to happen more quickly. It's going to be happier to do that. And that's because, remember, leaving groups are fine being stable on their own, so it's gonna be faster. Like if the leaving group is I And that's because I minus is really stable. It's a conjugate of a strong acid. Okay, then polar A product solvents increase the rate of E2 reactions. So, so something like the DMSO and other things that we've talked about in class will help make it go faster if it's got an OH in there or an NH in the solvent itself. It's just going to hinder it and slow it down by attacking that good, keeping the base from actually being able to react. All right, increasing rate. So tertiary is actually faster than secondary, which is faster than primary in terms of alkyl halides. And that is just because it's not trying to get in there. Remember, like with SN2 reactions, we had to like push our way in. So it was really hard for SN2 reactions to do that when something was really big like this. But all we have to do is take off a proton. Like that's it. So this thing just has to take off a proton that's way on the outside over here on one of these R's. And that's not a big deal for it to do. All right, the base appears in the rate equation because its rate equals K times the base, we just did it, times the alkyl halide. And the E2 reaction increases as the strength of base increases. So if you've got OH minus, it's about as strong of a base as you can have. So OH minus is fast. That'd be kind of the way I think about it. And then as you add more stuff to it, like that T-butyl hydroxyl thing, that's going to be, it was tert butoxide, but that's going to be a lot more slow. All right, so let's go ahead and summarize this. I didn't really write anything here, but I'm going to. So summary. So for E2, it's a second order reaction. It's done in one single step. It prefers the tertiary. In fact, instead of doing all that, I'm just going to write tertiary is greater than secondary is greater than primary. So it'll react with the tertiary again because it's not hindered. It's just trying to grab that proton. It prefers strong bases. And then if it has a good leaving group, it's better. And the thing about the leaving groups is that's true for SN1, for SN2, for E1, and for E2. If you have a good leaving group, the reaction is going to happen more quickly. Last but not least, it loves polar A product solvents. All right, so that is pretty much the summary of E2. Let's move on to E1. Oh yeah, the Zaitsev rule. You actually already know it. You just didn't know the name of it. And I don't like how this kind of fits between. I feel like this should have gone before, but because it works for both. And the Zaitsev rule, you are going to have the double bond between the alpha carbon and the beta carbon. That's going to give you the most substituted thing. So here we have a tri-substituted product because you look at either carbon. This is 1, 2, 3 carbons, and this one only has 2. So this is the di-substituted. So this one would be the major product. It's got more carbons around that double bond. And that's called the Zaitsev rule. All right, so if we were to predict the major product from this, we could put that double bond anywhere between an alpha and a beta, but the beta that I see that's the most substituted is right here, and my alpha would be right there. So the most substituted one would be this product right there. I kind of drew it funky, but it goes like that. All right, and you could very well get a minor product. I could have chosen my beta over here. So if my beta had been over here, so this was my beta 1 right there. If it had been the beta 2, oops, sorry, this is a pentane. It's gonna go like this. And it would have been off to the side over here, down here. Notice that this has fewer carbons around that double bond. This only has 2, whereas this one has 1, 2, 3. So this is the major. All right, let's move on to E1 reactions. So E1 reactions are unimolecular. Their rate only depends on K times the alcohol concentration. If you remember the first step in an SN1 reaction, you also know the first step in an E1 reaction. The leaving group leaves. So let's take a look at the mechanism here. Okay, so let's say you've got, I'm going to use this example that's down here at the bottom of the page. So let's say you have this thing. Ooh, look at that beautiful leaving group, right? Its first step is for that sucker to go. Okay, so in an E1 reaction, the first step is that goes. And guess what? You can tell already from the chart that that first step, where that thing goes, has the highest activation energy. Do you remember what that means? That means it's slow, but it also means it's the rate determining step. Okay. And that will give you the carbocation. So this would give us a carbocation that looks like that. Okay, let's go ahead and react that with, here in this example, it's reacting with water. And don't forget that when water is acting as a base, because you might be really tempted just to take this, throw it in there, and treat it as a nucleophile, but it's not. In this case, we're acting it like it's a base, and bases take hydrogens, right? So it might even be helpful for you to draw the hydrogens. This was our alpha carbon, alpha, and any one of these 3 could be the beta. It's gonna get the same answer no matter what. So let's go ahead and make this the beta. And it's gonna take one of the hydrogens on the beta. So this sucker takes a hydrogen, those electrons off the hydrogen come down. These electrons off this hydrogen go onto this double bond. And what you end up with is something like that. So the double bond now came down here, and that's why you get this looking thing. Oh no, somehow my phone went off. I lost you. I hope this was recording, but we'll find out. Okay, so just like in an SN1 or an SN1 reaction, in this E1 reaction, tertiary is going to be better because it's more stabilized. That carbocation is more stabilized by these R donating groups. So these help contribute and add stability to this one. And so the leaving group is more free to leave here, and therefore the reaction will occur more quickly. So this is also the same, if you remember, for the E2 reaction. So this is also the same for E2. The only time this is opposite is that SN1 reaction, or SN2 reaction. SN2. Okay. Zaitsev rule also applies for E1 reactions. So you want it to be more substituted. So we got the double bond here on the one that's going to be tri-substituted as opposed to this one, which is only di-substituted. Let's go ahead and see if we can form some products here. Okay, we don't necessarily have to do the mechanism anymore. We know it's a two-step mechanism where the leaving group leaves first. Let's just talk about what the products would be. So in this case, if we react it using some kind of base, we don't know which base it's going to use, we get something like this. And we'd have this. And the double bond can either go on this methyl group or right here. We know right there is more substituted, and that's where it's probably going to want to go, right? This would be the major product. But you would also get the minor product, where you do essentially that, where it would go on this methyl group right here. This would be minor. All right, let's do another one here. The leaving group would leave, the base comes in and attacks a hydrogen. This is the hydrogen it would most likely attack, or this. So actually, let's take a look at it. So draw your betas, if this is our alpha. If we got a beta here, and a beta here, this beta is actually more substituted, right? It's got three things around it. So let's make that 1, let's make this 2, let's make that 3, and let's draw all 3 products. So the first one, if it's between the alpha and the beta here, still have the methyl group there, you'd get that. So this would be if you're using the beta 1. If we use beta 2, then it's got to fall here between the alpha and the beta 2. We still have the methyl group there, and it would be there. And last but not least, we got this lonely beta 3, which would be a definite minor product in this. And it would look like that. So this would be with beta 3. This again would be the major. Okay, so let's summarize E1 real quick. It's very similar to E2, as you can tell, except for it just happens in 2 steps, and a couple other things are different. So first, it's a first order reaction. Of course, it has 2 steps. It prefers tertiary over secondary over primary alkyl halides, and that's cool because that's exactly the same as the E2. But because it's already got a positively charged thing, once the leaving group leaves, you're left with that carbocation. Weak bases work great for this. So weak bases are going to be the favored bases. Just like with E2, if you have a better leaving group, that's going to be better. And because you're going to be using a weak base, you want to make sure that you kind of hinder the leaving group that left, so it doesn't want to go back on. So to do that, you're going to use polar product solvents. Okay, we're on our last page, which is good because I got a meeting in 5 minutes. I can do this. We can do this. Okay, so now, oh, I missed this. Yeah, I was in a weird mood when I wrote, let's play a game called Is It E1 or Is It E2? I'll take I have no idea for $400. And then it's actually, they would both be formed. So as soon as leaving group leaves, it's open playing season for SN1 or E1. So let's talk about what would happen in both situations. In SN1, just to remind you, that's when the nucleophile is going to attack, right? So that OH is going to attack this carbocation after the bromide leaves. And you would have something like this, like that. It's just a straight up substitution reaction, right? And just don't forget, if this had been a chiral center, you would have had two different products. In this situation, if we do E1 and we treat water like a base, remember it's going to remove the hydrogen in the most substituted part. So it could be, so if this is our alpha, we put our beta there, our beta there, our beta there. These are both equivalent betas, so it wouldn't matter. So you'll get something like this. I'm just going to choose the beta that's right here. And that would be the major. And you'll get a more minor product where that beta's on that di-substituted one right there. All right, for this one, I'm going to draw the arrow down here. Let's go ahead and do SN1. SN1, remember, it's going to attack, it's going to attach, it's going to be a substitution reaction. So pretty much we just need to draw this whole thing. Plus an OH. But if we do E1, the double bond can either go here or it can go on one of these two methyls. So here or one of the two methyls. So let's draw them both. There's the first one. This would be the major product. And then the last one would be on one of those two methyls. Cool. So all of these would be formed. This one's only the major of the E1. We haven't talked about which one would be formed most and in which percentage. And generally, it'll actually depend on the molecule itself, but we'll get into it later. So, all right, plenty of time for me to go to my meeting. Hopefully everything I recorded, because at some point it stopped. All right, y'all, talk to you later. Have a great day. Bye.